CHEM152. This is chapter 12, which is the last chapter of new material. So your homework is out there, the last three homework sets. Please let me know if you got questions about exam 3. Last quiz coming up on May 14th. Exam 4 on May 19th. The review sheet's posted for that. Any of these things, come see me. Let's talk about it. Let's do practice. That's 9:35 a.m. using Zoom. And the theme for this last bit for sure is to finish strong. The end is near, so really encourage you, stay focused. There's been a lot of adversity this semester, but finish strong. I think you'll feel a lot better if you give it your best effort. Today we're kind of revisiting some things. Maybe just look at the titles: states of matter, solids, things that you've seen before, but now we're going to really go into some details that have been left out. So this is where we wrap up the semester. And if you look at the schedule, chapter 12, exam 4, then we have a full day to review. I'll assign a 10-point activity for that day, and this will help. The 10-point activity is to review for the final exam, and then you can see there's a week of exams for the final exam. Half will be multiple choice. That's part 2, 50 multiple choice questions. And part 1 is all short answer questions. And I'll talk more about that as it gets closer. So what we're going to see is we're talking about liquids and solids. And this is the new piece, intermolecular forces. So this is short IAM or IMFs. Intermolecular forces is the theme of this chapter, and we'll look at several ways that intermolecular forces affect things. First, I want to just talk about general electrostatic forces. Okay, so every molecule in a sample of matter experiences 2 types of electrostatic forces. We really haven't been talking about this terminology, electrostatic, but it's what holds things together. What's the attraction that holds things together? And mostly we've been talking about this, actually all of this semester, intramolecular forces, the forces that exist within the molecules. So is it a covalent bond? Is it an ionic bond? We did a lot of that. What's the Lewis symbols? What's the Lewis structure? So we did a lot on this intramolecular force, what bonds hold things together. And then we did the chemistry of those things, chemical reactions. So this is all intramolecular. What this chapter is focusing on is inter. So it's between molecules, okay? It's the attractive forces that exist between molecules. So now we're not just thinking about water, okay? That was before. What's the bond? These are sharing electrons. That's a covalent bond, okay? We're not just talking about one water molecule. We're saying what holds water molecules together. Why is water a liquid and not a gas? Why does that happen? So these are the dots that I'm showing here, is what we're talking about in this chapter, the intermolecular forces. And this, of course, just continues on and on for many, many water molecules. But the key, this determines the physical properties. So what we're going to see is that there's a variety of forces that are going to be described, but they all come down to that electrostatic. And so remember that electrostatic is charges that hold things. So what we're going to see is that there's full charges, like cations and anions, +1, -1. There's partial charges. So those are those polar molecules, partial positive, partial negative. And now we're going to be introduced to new temporary charges on molecules. So that's these intermolecular forces. Remember, we're talking about the forces between molecules. These are relatively weak versus talking about the bonds. Remember, bonds hold atoms together. So these are very, very strong, and they're short, right? 96 picometers, that's very short for a bond. This is a very strong interaction, strong bond. And now the intermolecular force between the water molecules is a much longer force, and that's a attraction that's weaker, but it's important, and that's what we're focusing on. So bond, force. I'm going to really emphasize those words as we continue. So this was some of the very early questions I asked. What is a solid? What's a liquid? What's a gas? How you describe those states of matter. So you would do a variety of things, but what we're going to see now is whether something is a solid, liquid, or gas. It depends on its intermolecular forces. It's all about the intermolecular forces. So we're looking at kinetic energy, how are things moving, the energy of things moving, and the forces that want to hold them together. So it's a tension, it's a battle. We've got kinetic energy, intermolecular force, okay? Intermolecular attraction. That's what's at odds here. So average kinetic energy of a sample is related to its temperature, so that's the thermal energy. So a gas, we've seen gases, we just did gas laws, and the kinetic energy of the molecules is much greater. Remember, those gas particles were separated out. They act like ideal gases because they're not affected by other molecules around them. So kinetic energy really wins out here for gases. Liquids, still kinetic energy is great. So that's overcoming, so there's lots of movement still. And the kinetic energy in solids is less than intermolecular attractions. So solids, the particles are really packed together, really attracted to one another. So you can recall then gases, recent that we did this, a lot of empty space, act independently. Liquids, still vibrations, still movements, they can fly off, get to evaporation, and then these solids have strong attraction, compact. So the differences are really distance. How far are these particles, which affects attraction? How attracted are the particles to each other? So that's the intermolecular force. That's what we're talking about in this chapter. And the motion of these particles, you can see the gas particles, if you imagine these going very, very fast and lots of freedom of motion. Solid, they're just vibrating, they're stuck in place. So those are the extremes for that. So that's revisiting our states of matter. Okay, so let's take a look a little bit more detail now, how that's going to relate. Liquids have high densities. We've seen this before. They have that indefinite shape, but they have a definite volume. Okay, so that's a review of what we've said about liquids. Solids, very dense. This is where we started with density. Density equals mass over volume. We did objects, the density of objects in lab on campus. They have definite shape, and there's not anything to compress because the particles are already so close. At the end, we'll talk about the two different types of solids, crystalline, amorphous. Sorry, these are two types, crystalline, amorphous. We'll talk about some different types of solids at the end of the chapter where we expand a little more on this. Effects of intermolecular forces. So if you didn't have intermolecular forces, the gas phase would be the only thing, okay? Because that's separated from each other. That is not interacting, not attracted. That's all that would take place. So clearly we've got intermolecular forces, and we have to look on the small scale to talk about the description of each intermolecular force, but here on the macro scale, the big scale, we can see some effects of that. The effects are clear in surface tension and viscosity. So we'll talk about those a little bit to really emphasize intermolecular forces. Okay, so surface tension. Well, more dense objects float. That doesn't make sense. Well, you've probably seen this before. If you can talk about this as like the skin of water, and you can see a fly fisher person here has got a fly on the water. It's floating. This is this skin of water, which is made up of intermolecular force. What does that mean? Well, if you take a look at the water molecules, they're being surrounded and attracted to those right next to it. Well, so I've circled this one and it's surrounded by 6 neighbors. Well, if we look at this one, it has a much different shape to it. That's only by 4 neighbors. Okay, so you can see now the tension, the pulling, where it's going is different than the one over here on the 6. So molecules on the surface are attracted to the molecules in the bulk. That's the pulling, that's what's going on, and it pulls the surface molecules inward and it minimizes surface area. Okay, that's the result of this skin that I'm mentioning. So that can resist penetration. Of course, you put a brick in there or something like this, it would overcome that, but this is the surface tension that we're talking about. And maybe you've seen this before too, like if you try and pour water out of a glass, if you do it really slow, the surface tension of water will stick together and dribble down the glass and make a mess. But if you break the surface tension, if you commit and really pour out the water, it'll go out, and then you pull back and it closes, it doesn't spill. So that's this skin or surface tension of water. The other one, maybe you've heard this term before, but viscosity. So that's a resistance of a liquid to flow. So of course that makes me think of food and syrup. It's, you know, especially if you keep your syrup in the refrigerator, it's really slow, it's very viscous. That's about intermolecular forces or attractions. That's what's holding them together. So viscosity, resistance to flow, surface tension, that's skin up on the surface. These are examples of intermolecular forces in action, and now we're going to talk specifically about each force. So I really want to emphasize again, I've already been talking about this, but these are forces, okay? Intermolecular forces. That's between molecules. This isn't bonds between atoms, this is forces between molecules. So we're going to go over the different intermolecular forces, and we're going to go in order here of strength. So it's dispersion, dipole, dipole. I put this in parentheses because this is called hydrogen bonding. This drives me crazy because remember, it's not a bond. These are forces, but that's the name of it. It's a hydrogen bond. Okay, so we'll go over these and talk about their specifics in pure substances. Okay, so what we're talking about is the dispersion force in pure substances, dipole, dipole in pure, and hydrogen bonding in pure. So the first one is dispersion, or what's called London force, and it's present in all molecules, and it results in changes in electron locations. Also want to mention, so molecules, that's compounds, or atoms, that's elements. Okay, so it's present in all of those. And this change in electron location, that's kind of strange, but remember we have orbitals, and remember electrons don't move like planets, so there could be a snapshot and electrons could be in this formation. We could have another snapshot here, they could be in this formation. Again, electrons are most likely in that region, but they could be anywhere in that region. But take a look at this one. Now you can see they've both ended up on this small section of the atom here, which if now we can see that's a buildup of a partial negative charge here on the left. Well, if you got a partial negative on the left, then you got a partial positive on the right. Okay, so remember this is a single atom. So now we're going to take this single atom and look at it as, wait a minute, there's an instantaneous dipole. Remember that partial positive, partial negative? So if that happens in 1, okay, so here it is again, 2 to the left, partial negative, partial positive to the right. Well, if this is a partial positive, then these electrons are going to be attracted to that positive. If those electrons are moved over there to form a partial negative, then there's a partial positive on this side. If there's a partial positive on this side, then again the electrons are going to be attracted over here, partial negative. So the instantaneous piece is, if there's a partial positive here, it affects these atoms around it. Partial negative, partial negative. So charge separation in 1 creates charge separation in the neighbors. That's the instantaneous dipole so you can see there's multiple atoms. That's why it's an intermolecular force. But remember, these are weak attractions. Okay, these are partial charges. These are weak attractions. So this is the weakest dispersion. And the strength of dispersion depends on polarizability. And what that means is, will these electrons move around like we just saw? Will the electrons move over to the left, partial negative, and have a partial positive on the right? So large atoms with large electron clouds have stronger dispersion forces. They're more polarizable. Large molecules tend to have stronger dispersion forces. Okay, so that's molecules and atoms that we're emphasizing here. So let's take a look at some examples. Here are our noble gases, and remember on the periodic table, as we go down, they get larger, and you can see here the masses increase. And what's being shown here is the boiling point. Okay, remember, states of matter, boiling point is the liquid going to the gas. Okay, so if atoms want to stay together, if they have strong attraction, then they're going to have a higher boiling point than if they have a less attraction to each other. So you can see here 165K is the highest, and that's xenon, which is the largest and the heaviest. So the stronger attraction goes with the larger atoms here. The next intermolecular force is dipole-dipole. So if we have a dipole, that's telling us that this is from polar molecules. Okay, so polar molecules, they already have partial positive, partial negative. Those are permanent dipoles. It doesn't have to be created. So if they have permanent dipoles, there's going to be attraction. Okay, so remember, we're not going to ever have a sample of one molecule, partial positive, partial negative. Even if we had one sample of that, even if we had 1 mil sample of that or a 10 mil sample of that, there's many, many of these molecules. So what are these molecules doing? They're lining up, partial negative, partial positive. That's a dipole-dipole interaction. So the effect of this, if we're having polar molecules, they both have dispersion forces and dipole-dipole forces. But we can definitely see this in boiling and melting points, just like we saw with the boiling point of the noble gases. Take a look here. This is formaldehyde and ethane. Okay, and if you can see, their mass is relatively the same, 30.0, 30.1. However, this is a polar molecule. This is a nonpolar molecule. So what forces do nonpolar molecules have? They only have dispersion. And what forces do polar molecules have? They have dispersion and dipole-dipole. Okay, so if we look and see then, I know these are negative numbers, but negative 19 is a much higher number than negative 88. Negative 92 is a much higher number than minus 172. That's showing that this dipole-dipole force, along with its dispersion force, is a stronger attraction than just dispersion force. Here, this dispersion force is weaker, so that's why we have these numbers here. So that's dispersion and dipole-dipole. Now let's talk a little bit about how these intermolecular forces interact for solutions. So you might have heard the terminology before, like dissolves like. What does this mean? Well, polar liquids are miscible or will dissolve with polar liquids. However, that will not be the case with nonpolar liquids. Okay, so like dissolves like means polar wants to stick with polar. Nonpolar wants to stick with nonpolar. Polar and nonpolar do not mix. Miscible means it's mixing without separating into two phases. So the salad dressing here you've seen definitely has two phases. This is nonpolar and polar water, doesn't mix. This is an oil spill in water, doesn't mix. So there's two distinct layers. All right, so let's look at the third intermolecular force. And again, it's a force. The name of it's hydrogen bonding, but it is a force. It is between molecules. That's what we're looking at. So it's not a bond, okay? So don't think of it as a bond. Actually, you can think of it as a dipole-dipole force, but it's actually just a special dipole-dipole force. I call it a super dipole, okay? Why this is the case is because it occurs between hydrogen, and when hydrogen's bonded specifically to nitrogen, oxygen, or fluorine. So that's the super piece, because remember, fluorine is so electronegative, so that's a good example to look at. Fluorine is so electronegative, so this is a big partial negative. That makes hydrogen partial positive. And because these atoms are quite small, now we can have another molecule, because remember, that's what an intermolecular force is, another molecule interacting. So this is really close because the size of these are small, and because the partial charges are so great, that's why it's super. That's hydrogen bonding. Well, this occurs often in things that you're familiar with. So water, ethanol, here partial positive on hydrogen, partial negative on oxygen. This is ethanol, and this is a really common example seen water, and you can see water has two hydrogen bonds coming off of this one water molecule. So this is intermolecular forces, and remember the bonding is the actual atoms. That's what's a bond. I know this is called a hydrogen bond, but it's an intermolecular force. And it's a very strong intermolecular force. So let's take a look at that. This strong intermolecular force, it has water with a much higher boiling point than expected. So water is significantly higher than it should be for such a small molecule. And that's the same with this here. You can see again, 30.1, 32, so very similar masses, but methanol has hydrogen bonding and has a boiling point of 64.7 versus ethane with a minus 88. So very different because of hydrogen bonding. Hydrogen bonding, maybe you've also seen in DNA, so you can see here the way the bases match up, 2 hydrogen bonds or 3 hydrogen bonds. Those are intermolecular forces that connect this double helix. So those are the intermolecular forces of pure substances. So I was showing you attractions between one thing to itself, water, hydrogen bonding to water, ethanol, hydrogen bonding to ethanol. So now we have a mixture. Okay, how do we know this? Well, the title gives it away. Ion, that leads us to ionic compounds. And dipole, we've already seen in dipole-dipole, that leads us to polar substances. So an ion-dipole interaction is now a mixture of an ionic compound and a polar compound. So this is aqueous solutions you've been working with all semester. Chloride would be surrounded by the partial positives of hydrogen. Sodium would be surrounded by the partial negatives of oxygen. That would form a solution. Like dissolves like. These are close enough, ionic and polar, that it forms a solution. So to summarize then, you want to be familiar with the forces. So on the left are the name of the forces, going from weakest to strongest: dispersion, dipole-dipole, hydrogen bond, ion dipole. And then you want to be familiar with what are some compounds that have these forces. Okay, so any substance has dispersion, but particularly nonpolar compounds like hydrogen, H2, that's the only force that exists between those molecules. Here, HCl is an example of a polar molecule. HCl has dipoles, so that's dipole-dipole attraction. Remember, fluorine was one of our examples of hydrogen bonding, so it has to be FO or N. And remember, the hydrogen has to be bonded to those. So just because you see something with hydrogens Okay, so we've seen methane, CH4, quite a bit this semester. You can't look at methane and say, oh, methane's got hydrogens, that's hydrogen bonding. Well, it depends. The first in our rules are the hydrogen has to be bonded to fluorine, oxygen, nitrogen. That is not the case here. The main thing it comes down to is it a polar compound? And this is a non-polar compound. So there's no partial positive on hydrogen. There's no partial negative on carbon. So this does not have hydrogen bonding, even though it has hydrogens. So this is a specific case here for hydrogen bonding. And then our mixtures, ionic compounds and polar compounds are good examples of this ion dipole attraction, as you can see here with the cation surrounded by water. So these are the intermolecular forces. This is the key to this chapter. And this is what it would look like. You'd be given substances. Okay, these substances here. So this is really a cumulative question. This goes back to a lot of chemistry that you learned throughout the semester. Determine the kinds of intermolecular forces that are present, and I would write this now as the strongest force that is present. So go ahead and pause this and think about the force, see if it applies to each of these. So what I want you to do here is to think about what compound this is, what kind of compound. Okay, so this isn't an ionic compound. This is a polar compound, and if it's a polar compound, that has dipole-dipole interactions. If you look here at iodine, that is an element. It's a diatomic molecule, but it's an element, so it does not have a dipole. It's not a charge. It's not an ion. It doesn't have a hydrogen, so you're left with dispersion. Carbon monoxide is a molecule, and it's a polar molecule. There's no hydrogen, so there's no hydrogen bonding. That's dipole-dipole. Ammonia is NH3, and this would take us back to what's the shape. That's a trigonal pyramidal shape. That's a polar bond, which makes this a polar molecule. Oh yeah, and hydrogen is bonded to nitrogen. That makes it a special dipole-dipole. It has hydrogen bonding. And then lastly, this is a covalent compound, so it has dispersion. So as I mentioned, really important to be able to know the intermolecular forces and then know how they apply to substances. Does it have dipole-dipole? Does it have dispersion? That's what I want you to look at for this. The last two slides I want to touch on is going back to that solids that I mentioned. Okay, so there was amorphous and crystalline solids. So crystalline solids has a repeating pattern over and over again. Well, there's actually three types of crystalline solids. Okay, so if we look here, there's molecular, made up of molecules, covalent bonding. There's ionic, made up of ionic bonding. And there's atomic solids, made up of elements. Okay, so if you look, these vary pretty significantly. So molecules, that's what makes up covalent compounds. And they're made up of these weak intermolecular forces, so they have low melting points. Okay. On the other hand, ionic solids are made up of cations and anions. They're made up of ionic bonds throughout the full solid. That means that strong attraction that has high melting points. Atomic solids, this is a little bit more confusing because it's definitely made up of atoms. However, there's a range of atoms and properties. So we actually go to the next slide. So atomic solids, we pick up here, and now atomic solids is at the top. So atomic solids can actually be covalent, non-bonding, or metallic. So covalent, silicon's an example, carbon diamond's an example, that has very high melting points. Okay. If it's just weak dispersion forces that are holding things together, so there's not any covalent bonds, that's low melting points. And then lastly, metallic bonding, we don't really talk about much in our chemistry classes, but metals are all around us, so it's kind of left out. But metallic bonds have variable melting points. Some metals will actually melt in your hand if you hold them, and then some have higher melting points, and so on. So So this is the end of new material. Please see me during office hours if you'd like to talk about Chapter 12.